Thank you for coming back. It's a great pleasure to be giving this talk. What do I want to say? I guess I want to tell you about some small results, basically. Like this was a talk given in an attempt to be on theme rather than to like present super cool things. And I love questions. So if you have questions, please interrupt me. So yeah, great. So first of all, what's a virtually free group? Well, so in our parlance, our lingo, a group is virtually blah if it has a finite index blah subgroup. But since subgroups of free groups are free, a group V for virtually, I guess, is virtually free. And for this, this can be a definition for us. If and only if, well, I almost wrote IFF, and I hate writing IFF, so I won't. There exists a short exact sequence with F a free group here, V my virtually free group, and Q finite. So Q is finite. Q finite, and F free. Okay, great. Let me get rid of this little thing. Yeah, what to say? So right. So you know, formally, right? It just means we have a finite index free subgroup, but every finite index subgroup contains a finite index normal subgroup, and subgroups of free groups are free. Hence, I can take a normal finite index free subgroup. Great, cool. Oh gosh, okay, cool. So it's a theorem of Karrass, Pietrowski. Pretty sure that's how you pronounce the W. And Solitar from the 70s, 73, that V is finitely generated and virtually free. Ooh, good. Virtually. If and only if there exists a tree T with an action of V with finite stabilizers. And finite, i.e. compact quotient. Great. So these are just the groups that act geometrically, if you'd like to give them a metric, on trees. Cool. So the quotient, which I'll put in quotation marks for reasons that I'll explain in just a second, of T by my action of V, and I'm doing this double backslash for the same reason that I'm putting quotation marks, so I'll tell you now, is a finite graph through it. But it's a graph of groups, but they're finite groups. So it's a finite graph of finite groups. Right. So Daniel mentioned this in his talk. A priori, you have to worry about like, you know, fixing a cell but not fixing it pointwise. So maybe you like have some automorphism of your tree that like flips an edge. I don't know. I'm doing this over here. This is sort of where you were when you talked about it. And you can fix that for trees by just passing to a barycentric subdivision. I'm going to sort of like, I don't know, assume that you did that, or maybe like not. It doesn't super matter to me. What I care about is the action on the tree qua like a metric space, I guess. So if so for me, really, I care about the action on the metric space, which turns out to respect the sort of natural simplicial structure that you can give it, but whatever. Great, cool. So let me give you some examples. I have 3, and I have colors, great. So I'm gonna draw the graphs of groups, and I don't know, I like to like, I remember when I was like an early grad student, I was like, people were like, Basser tree, and I was like, what is that? So I wanna give you some idea of like what that means. Okay, so this one's going to have, my graph is going to have 2 vertices and 1 edge. Here's my edge, great. I need to assign groups to my vertices and my edge. The edge is going to get a cyclic group of order 2. So if you're like me and you work with somehow finite groups a lot, C sub 2 is so much faster to write than Blackboard bold Z mod Blackboard, yeah, whatever. So C sub 2 for cyclic group of order 2, great. This edge group, sorry, this vertex group is going to get the Klein 4 group, so the product of 2 of those, And this one's going to get the symmetric group of on 3 letters. So S3. Great. Okay, cool. So that's one. And then I'm going to draw the Bassett tree after I've given you of this guy, and then maybe also this guy that I haven't drawn, and this one too. Great, cool. Okay. So this one's going to have 4 vertices and 3 edges. So it's a tree. Here's one edge. Here's edge 2. And then, I don't know. Here's edge 3. Blue isn't maybe great. I'll just do that once. It's not super important. I'm going to give cyclic groups of order 2 to these 3 vertices. Everything else is going to get the trivial group. I'm really lazy. I'm just going to not write anything. Hopefully you can forgive me. And then here's another graph. And it's got 2 vertices, 3 edges. So it's not a tree. And it looks like this. It looks like a theta. And I'm going to give the trivial group everywhere. Okay. Cool. So these are graphs of groups. So the Bassett tree, there's a very simple formula to draw it once you have the quotient graph of groups. If there's nothing here, then it's just drawing the universal cover of a graph, which is something that we learned how to do in algebraic topology. So I won't do. But for something over here, I need basically, I know what the stabilizer of this vertex is. It's given to me. And I need to know about kind of the action of that on the edges incident to that vertex. And these are just sort of like discrete sets, like they're edges and they're sort of being permuted in some way. And so the only action is really the action of a group on the set of cosets of some subgroups. And here, my subgroup is the cyclic group of order 2 sitting inside the, or one way of it sitting inside the symmetric group of on 3 letters. So what can I say? I can say that there wants to be up in the Bassett tree 3 edges here because this subgroup has index 3 in here. Great. I'm going to draw 3 edges incident to this edge. And then I sort of mark this guy as done. And I have new vertices at the end of this edge. And I go visit them and I ask, what do I need to do? Over here, well, this guy, the edge group has index 2 in the vertex group. So I need another edge here and like also here and also here. Great. And then I can keep doing the thing. And so I mark these new vertices as done. And I have some sort of like inductive limit process that draws the tree and this works in like full generality. I guess, yeah, maybe you need to be a little careful about what if this had like more stuff over here? I don't know. But it's okay. And if I have loops, like maybe I need to take the universal cover of the graph qua graph and then like do the same thing. I don't know. It's okay. Cool. And I'm claiming that actually, if I do the same process over here, I get the same tree, even with the, the subdivision of these edges into like this really wants to be one edge, but maybe it's inverted or something. So it's the same tree. The difference is the action. This action had 1 orbit of edges, and this one will have 3 orbits of edges. And yeah, maybe that's all I'll say. And this one, like, it's really the same tree too, except you have to maybe subdivide this guy or unsubdivide this guy to get the same thing. And actually, I don't know. I sort of like saw that this was happening and then like made it not an accident. But this was sort of accidental. But it turns out that the fundamental group of this, right? So what's the virtually free group here? It's just the free product of S3 and I'll write V4 for the Klein 4 group along a cyclic group of order 2 amalgamated. So it's an amalgamated free product. This one, my group V, is just the free product of 3 copies of the cyclic group of order 2. And then this one's just F2, right? The free group of rank 2, which is a virtually free group. Yeah, great, cool. Yeah, what to say? Oh, and I guess like if they have the same universal cover, in fact, these groups like this one's a finite index subgroup of this guy, and this guy is a finite index subgroup of this guy, and so transitively, of course, too. Great, cool. So these are closely related groups. Yeah, cool. Virtually free groups, vast hair trees, awesome. Okay, so I want to tell. So that's like this half of the talk, right? No. I want to tell you about outer space. And so first of all, it's not that outer space. So it's a pun. It's a space for the outer automorphism group of blah to act on. And in this case, it's the virtually free group. So outer space for V, I'm going to call it, I don't know, fancy P, T, V. P for projective, T for tree, V for V. Great. Is it's a deformation space. So if this means something to you, it means something to you. If it doesn't, it doesn't. Space of trees, of really metric trees. So I said earlier that I was going to think of these things as metric spaces. Metric V trees, so they have a V action. Such that, first of all, the action should be minimal. You're in, if you're here last week, JP mentioned minimality. What I want is that, like, well, it's really a dynamical systems thing. I don't want an invariant subdynamical system. I don't want a subtree that's invariant into the action of V. So it's minimal. I want stabilizers are finite. And it turned out that's it. And then I'm going to consider these up to, so modulo, the equivariant homothety. Homothety? Who knows? Not me. So in other words, so it's a metric on a tree. It's just an assignment of length to edges in some sort of group equivariant way. So it's really an assignment of lengths to edges downstairs on the quotient. And what I want to say is that, like, scaling the length of each edge by some positive number shouldn't affect what I'm doing. So what I'm saying. And then this is a space that's got a topology. And the topology is sort of, it's like stretching and squashing. Let me just draw you a picture. And then you'll be like, great, you don't need to tell me what the topology is. So here's a picture of outer space for this guy, the free product of 3 copies of the cyclic group of order 2. So what I've drawn for you now, none of these points that I drew in the circle are in the space. I'm sorry. It's just sort of like how when you try to draw the hyperbolic plane, you draw its boundary. That's what's going on here. Okay, so I'm drawing triangles. I'm going to stop at some point. This should look suspiciously like the fairy tiling of the hyperbolic plane. That's intentional. And then I'm going to add, so I have the fairy diagram. That's what I'm drawing. And then I'm going to add fins to every edge. The sides of the fins are not in the space, but everything else is, okay? So these are sort of like ideal simplices. They're like missing their vertices, and these ones are actually missing their edges too. Okay, I think that's sufficiently unclear, so I'm going to not keep drawing. But instead, I'm going to sort of tell you what these points correspond to, except I'm not going to use blue, because I don't think it carries. Okay, great. So a point in here corresponds to a tree whose quotient graph of groups looks like this. So it's a trivalent tree. So I got a C2, a C2, a C2, a free vertex, 1, 2, 3 orbits of edges. And that's not an accident, right? The reason that this sort of ideal simplex is 2-dimensional is because I have 3 parameters, right? The lengths of these 3 edges. And then if I'm considering up to whatever this word is, I have 1 constraint. So that's a 2-dimensional simplex. It turns out the boundary edges of the simplex belong to the space. So here's one of those. Maybe this corresponds to collapsing the red edge. So I get a graph of groups with 3 vertices all with non-trivial vertex group C2, and then 2 edges. Great. And this fin here, also in the space, sort of pesky. This is sort of a silly graph of groups. It's got, okay, I'm even drawing it a little funny. Orange and yellow. The orange and yellow edges have trivial edge group, but the red edge gets a cyclic group of order 2. I can't rule this out. It exists. You could rule it out by, like, you know the words, passing to the reduced outer space. Okay, there's like a deformation tract that, you know, gets rid of all of these fins, and you get the fairy tiling, which is sort of nice. But this thing exists. Cool. If you noticed, like if there's kind of like there's a finite index subgroup of the free product of 3 cyclic groups of order 2, which is a free group of rank 2. It sort of looks like you branch over these fixed points. So these things give me theta graphs. These things give me roses with 2 petals. Yeah, harder to see, but still true. These things give me dumbbells. Yeah. So, so is this like yep, and it turns out it's everything. Yeah, it's the whole thing. And that's the you're stealing my punchline. That's what I'm saying. No, that's great. Oh yeah, I guess, yeah, let me just tell you what the action of, right, so there's a group acting, right? I don't want to consider this space for no reason. Where am I gonna, I'll erase over here. So the group that most naturally acts, I guess, is the group of automorphisms of V. I'm sort of prejudiced. I don't really like automorphisms as much as I like outer automorphisms. And it turns out the group of inner automorphisms acts trivially. So I get an action of the quotient group. So that's sort of nice. Okay, great. So if I have an automorphism of V, my virtually free group, and a tree. So really this is an equivalence class of trees. Whatever, just take the tree, okay? You could, if you wanted, like normalize by doing some volume construction. I'll tell you the proper way to do that in, I don't know, 10 minutes. Okay, great. So I get a new action of V on a tree, T. It's the same tree, but I'm calling it T hit phi, I guess. So it's the same tree with the action. Right, I'll be very, very clear. What's an action? It's a thing that sends a group element and a point to a new point. And the new point is I apply the automorphism to the group element, and then I act by the old action. Okay, so this is sort of like phi twisted equivariant. Inner automorphisms of V correspond to equivariant isometries of T. So in the end, I get an action of the outer automorphism group on my outer space. Great. Yeah. I'm going to give up using the nice chalk because it's too short now. Okay, so I'm going to tell you the theorem that Genevieve anticipated. Yep. Oh, just it's more than the quotient graph. It's the quotient graph of groups. Yeah, that's all I meant by the scare quotes. Yeah. Yeah. Okay, so theorem of mine from last year, inspired by work of Spencer Dowdall and Sam Taylor from 2017. Let me get the statement right. Yeah, okay. So if one nice thing about using, I don't know, I don't really use V for groups very often, but one nice thing about using V is that there's a nice finite index subgroup sitting there, which is W. So if W is a finite index subgroup of V, Then for every tree in the outer space of V, W acts on T. And this action is minimal. Stabilizers are finite. So this is really giving me a point in the outer space of W. So in what Genevieve was talking about, when I take my sort of cyclic branch cover or my order 2 branch cover of these things, and I'm getting a free group of rank 2. Yeah, this is that's exactly the setting that you should be thinking about. So this defines map, I'll call iota, from the outer space of V to the outer space of W. And the conclusion is that iota is an isometric embedding with respect to, well, it's not a great metric. It's, well, I don't know. It's lovely for some things. The asymmetric, you should be going, what? Lipschitz metric. I'll tell you about this like sort of towards the end. And it sends a nice class of directed geodesics called folding paths, which I probably will not tell you about, but we'll see. To folding paths. Moreover, yeah, just in like, yeah, so I'll say moreover, if Q is like if you're so lucky that maybe I just won't say this. Never mind. I'll say this later. So one thing that was nice about the case of the free group, setting aside the free product of 3 cyclic groups of order 2, is that it's a normal subgroup. So I get a quotient, and the quotient group, which is cyclic of order 2, it turns out, acts on outer space for W, which in this case is the free group of rank 2. And this turns out to be the fixed point set for that action. I'll mumble things to that effect, but I won't write that here, I guess. Cool, great. Oh, maybe yeah, okay, great. So I'm mumbling things to that effect now. Awesome. Cool. So, great, okay. Yeah. So if I'm so lucky that I get maybe a normal free subgroup of finite index in my virtually free group, so I get a finite quotient group, Q. So I'm using the notation that I used all along. Conjugation in V induces a map, I'll call it alpha, from Q into out F. So I don't need F to be free here, but like this may be the most interesting case. So I'll write F and we'll pretend it's free. Great. Then I can do a thing. I can let W, that's what I'm calling it. I am calling it W. Be the collection of automorphisms of F. So this is like the full preimage, really, such that the outer class of phi lives in the image of alpha. So this is the full preimage of alpha of Q and out of aught of F, sorry. W is virtually free. This is hopefully clear. In fact, you can show using something about subgroups of like direct and fiber products called Gorsat's lemma. That says that V turns out to be isomorphic to the fiber product of W and Q over alpha. So if I take a thing in the quotient group and a thing in W, whose image when I either pass to outer automorphisms or I apply alpha gives me the same thing, that's actually all of V. So this is sort of the only game in town in terms of constructing virtually free groups, is you have maybe subgroups of out of a free group and finite groups that, you know, surject onto that, and you play some sort of combination game using fiber products. Cool. So I bring this up because I want to kind of restrict to the case of like W. So the thing that really comes from the image of some finite group into out of F. Okay, cool. So this next theorem is kind of, or I don't know, it's going to take me a bit to state. But if you know something about mapping class groups, and I'll sort of mumble more things as I go, this is kind of like a Berman-Hilden type theorem. Although I don't know, I'm still a board away from stating it, so we'll see. So if alpha is a homomorphism from a finite group into the outer automorphism group of, say, a free group F, I can look at, well, first of all, there's like sort of somebody called this like a universal extension of F. So the free groups have no center, great. So they're isomorphic to their inner automorphism group. They inject into the automorphism group. I'm going to call this map to the outer automorphism group PR for projection. Great. And I can look at as well, I have my F to, okay, over here I called it W. I'm going to start calling it V. I hope that's okay. Just following my notes. Alpha of Q1. So you should really think if you're looking over here and you're going over here, V is W, okay, yeah. So there's a map here. This is injective. This is an isomorphism. So this is injective, yeah. That's the 5 lemma. Great, cool. So I can look at the normalizer of this guy in here. I'm going to call that N of alpha of Q. This is the normalizer. And then for secret reasons, I'm going to introduce another subgroup. I'm going to call it aught0 of V, which is those automorphisms. So automorphisms such that phi really preserves F. It's maybe not the identity on F, but it at least preserves it as a subgroup. And oh yeah, out 0 of V is just going to be the image of aught0 under projection. Great, cool. Great, okay. The other theorem that I want to tell you about goes like this. And this was fun. I don't know. Yeah, this one's the most fun I've had doing just group theory. So I want to actually sketch the proof of it for you because it's not hard. And as I say, this is sort of like a special case of a theorem of Berman and Hilden for mapping class groups in the case where you have like I don't know, like a regular branch cover. That's kind of the thing to keep in mind. So the theorem says there exists a short exact sequence. One goes to alpha of Q, goes to its normalizer out, yes, of F, goes to out 0 of V, goes to 1. And if, I just want to point out, if F happened to be characteristic in V, I could take a further finite index subgroup that does this. So it's not an onerous restriction. Then this is everything. So this is everything. So if F is characteristic, then out 0 of V is really all of out of V. Cool. So the proof sketch will be somewhat sketchy. That's okay. I need one more, sorry, apologies. I need one more group. It's not gonna, I'm gonna call it M, and it's gonna be the inverse image under projection of the normalizer of alpha of Q. So this is, so this is a subgroup of the outer automorphism group of F, and this is a group of automorphisms. Okay, fine. You're going to see why this is the most fun I've had doing algebra in quite a while. So what do I know? I have like given to me this short exact sequence. Great. And I have an injection from V into aught of F. In fact, I have an injection into aught 0 of V because F is normal in V. Yeah, so conjugation of V acting on itself does preserve F. Great. Okay. The hard part, and the part that I'm not going to, well, I don't know, it's not that hard, but the part that I'm not going to show you is that this is an isomorphism, so I get to put 1 here. So this is injective. This is injective. The kernel here is alpha of Q. This, the quotient is the normalizer, right? That's how this is defined. This quotient is out 0 of V. That's also how it's defined. And this quotient is 1. When the images of these homomorphisms are normal subgroups of the down here, which they manifestly are, the snake lemma applies. So you have to do this. And that's exactly what we wanted. Proof sketch complete. Very fun. Okay, cool. Oh, I'm making great time. So I can tell you about the Lipschitz metric. Wonderful. Yes, please.
Can you give an example? Maybe like if out the threefold product of C2 or interesting.
Yes, it's isomorphic, it turns out. So the yeah, so the right. So how does this go for? Yeah. Let me give an example. In orange for no reason. Right. So right. I have my free product of 3 cyclic groups of order 2. Free product. Great. C2. It's got a finite index normal subgroup. That's actually characteristic, which is F2. And this guy here is a cyclic group of order 2. Its image is the hyperelliptic involution of the free group of rank 2. So this is the cyclic group of order 2. So this I said it was characteristic. So this is actually all of out of whatever the free product of 3 copies of the cyclic group of order 2. Great. And the normalizer, this is central in out of F2. So the normalizer is actually all of out of F2. So that's what's going on in that particular case. You lose this if you move up from, like, you still have like a cyclic group of order 2 here and a free product of however many copies you'd like of the cyclic group of order 2 here, but you lose the fact that the normalizer is everything. So you get a smaller group, which is also analogous to what happens for mapping best groups. Yeah. Other questions? Lipschitz metrics. Cool. Let me not attempt to steal this chalk. Where did my eraser go? It's right here. Cool. Okay. Simple Lipschitz metric. Okay, great. So suppose I have a tree T and it's in the outer space of V. V, we're going back to just being a general virtually free group. I'm putting in quotation marks because really this is this represents an equivalence class and yada yada yada. It's gonna be okay. I'm gonna take a genuine tree though because I need to for this definition to make sense. So define the co-volume. Danny, at some point I want to know what, like, if I just wanted to write the symbol instead, do I underline the symbol or do I just write what it is and then? Yeah.
Thank you for reminding me.
Yes. You're very welcome. So the co-volume of T, otherwise known as the volume of the quotient graph of groups, is by definition the sum over, you could say edges of the quotient graph of groups, or you could say orbits of edges up in the tree. Either's fine with me. of the length of that edge, yeah, L of E, great, divided by the order of the stabilizer, which I'm going to write as script G sub E, script G just for graph of groups. I don't know, I'm sort of attached to this notation. Great. So it's just the length divided by the stabilizer. This is sort of, I don't know, this is important and it was missing previously. Granted, in previous like studies of the Lipschitz metric on deformations of spaces of trees, which are not outer space for the free group, you're generally interested in having maybe this be an infinite group. So I can see why it was missing, but it was missing nonetheless. Okay, cool. So this is not the Lipschitz metric, sorry. It's going to take me a bit. That's why that's not on the underlined, that's why it's boxed. So given T and T prime, both in outer space for my group V, well, the reason that they're in the same deformation space is that there exists a V equivariant map F, which I can take to be piecewise linear if I'd like, and I would like, V from T to T prime. And okay, it's piecewise linear. There are finitely many orbits of edges. So I can ask what's its Lipschitz constant. So its Lipschitz constant, lip of F, is finite. Great, this will be helpful. Awesome. So again, I guess I ought to put quotation marks here too. I'm about to write down something that really depends only on the homothenity classes of T and T prime, but it's not defined that way, I guess. So the Lipschitz, I don't know, maybe the Lipschitz displacement is one word that I've seen for this, is going to be, by definition, the infimum over all maps F of the following quantity. I'm going to take the co-volume of T, divide by the co-volume of T prime, and then take the Lipschitz constant of F. So yeah, maybe I could like scale my guys so that this Lipschitz constant is 1, but then that sort of is offset by this thing. So they're sort of correcting for each other. Great. And okay, so oh yeah, so note well, this depends only on, I'll say the classes, the homothenity classes of T and T prime genuinely in the outer space of V. Cool. Great. So the Lipschitz distance from T to T prime is, well, it's a, I don't know, it's, so from T to T prime is you observe that like Lipschitz constants multiply, and with this correction and this like good notion of volume, it turns out that like this infimum is 1 if and only if they're the same point. And so you say, okay, so great. So my distance is going to be, given those observations, the log of the Lipschitz distance. Okay. Great. Cool. So the proposition, which in this generality really goes back to minor, involves the precise amount of my contribution is to say this is what volume is. Okay, so it's not a lot, but it's enough. And who else? For free groups, this was really developed by Francavilla and Martino, building on oh, hang on, Tad White. I was going to spell it with a Y, but I think that's somebody else, so I'm not going to. I hope I'm not misspelling Tad White's name. So this was his PhD thesis. So several facts are true. First of all, the infimum, maybe infs make you a little bit nervous. It's really a minimum. Okay, so that's great. Minor proves this using non-principal ultrafilters. Hadway proves this using the Arzela-Ascoli theorem. Our trees are locally finite. You should be able to prove it with the Arzela-Ascoli theorem, but non-principal ultrafilters are fine. The Lipschitz displacement between two trees is also equal to the supremum over group elements, which are hyperbolic, so they act, loxodromically on some and actually hence any tree in the outer space of, again, I have this correction term, the covolume of T divided by the covolume of T prime times, yeah, I guess it's psychological. The translation length of G with respect to T prime divided by the translation length of G with respect to T. Okay, so if I'm not super comfortable with like Lipschitz constants of piecewise linear maps, maybe I could just say, okay, maybe I can count or see how far hyperbolic elements translate me. And then maybe you're worried about the soup, but it's a max. It's a max over a finite set. Minor produces an enormous finite set, and I reduce it down to a manageable size. And this distance is positive. The distance is 0, right? This is my contribution, I suppose. If the equivalence classes of T and T prime are the same, and there's a triangle inequality. So the distance from T to T double prime is less than or equal to the distance from T to some intermediate tree T prime plus the distance from that intermediate tree T prime to where I wanted to go, T double prime. But notice I didn't say anywhere that this is symmetric. It's not symmetric. It really genuinely is not symmetric. One way to think about this is that it's easy to shrink things and hard to make them grow big again. Like I could maybe, yeah, I don't know. Suppose I have some small subgraph over here that I want to make really small. I have to do something with like the volume that it was contributing, but maybe I could like spread that out sort of nicely among everything else. And maybe I'm not even changing the like combinatorial type of my graph while I'm doing this, or my graph of groups. So I could do that. And then to get back up, it turns out the thing that I made really small is the thing that gets stretched the most. So it's whereas it was not contributing to the Lipschitz constant of the shrinking map, it really is contributing to the Lipschitz map of the Lipschitz constant of the growing map. So that's why we're not seeing symmetry here. I would love, yeah, one of my favorite questions is there a nice sort of natural symmetric metric on outer space? So if you have ideas, I'd love to chat to you. I have like maybe a couple minutes, so maybe I'll mumble things about holding paths. Is that what I'm going to do? That's what I'm going to do. I'm going to mumble. Great. Oh gosh. Okay. What do I want to say? Actually, yeah, I don't know. We'll see. Okay. So let's revisit our free product of 3 copies of the cyclic group of order 2, I guess, again, because why not? Oh, okay. So, right. I'm thinking about how I don't want to scare you too much. So maybe it's easier to think up in the tree. This tree is, well, it's, I guess, bipartite, although there are 3 orbits of vertices. There's this guy whose valence will have, let's practice, valence 4, yeah, 2 times 2. Ah, great, 4. And then these guys will have valence 2, right? 2 times 1. So it's a 4-valent tree, I guess, if you'd like. Great. And what do I want to say? I guess I want to sort of try deforming this tree. So let me draw the tree instead of the graph of groups. Oh, man. Oh, ooh, yikes. Let's fix that. Great. Rob very kindly said that I said that we should all draw the trivalent tree, and here I am drawing the 4-valent one. Good. Okay. And let's suppose I want to get somewhere else. So how do I move around in this space? That's kind of really what I wanted to convey in my last couple minutes. It turns out the best way to move, one way to think about it is I want to move in such a way that my Lipschitz constant is 1, and then I'm letting my volume do whatever it wants to do. Okay, so if my Lipschitz constant is 1, I'm like a distance decreasing up, and if I'm piecewise linear, maybe I could just be an isometry on each edge. Okay, so that would be something that is Lipschitz constant 1. So there are obvious ones that do nothing, right? But I want to actually do something to this tree. And one thing that I could start doing is I could start taking little pieces of edges and start like identifying them together. And I want to do this in sort of an equivariant way, which I think forces, if I'm not mistaken, me to also be doing this because I have secretly finite group of order 2 acting at that vertex. Yeah. And then I'm doing it equivariantly, so I kind of have to do it everywhere. Okay, great. So if I do that a little bit, I get a new tree. And maybe it starts looking like, what did I draw? Yeah, it starts looking like this. And then, so this is the bit that like was here that's like getting identified. Yeah. And then it starts being separate again. So now I get a trivalent tree. Oh, I guess whatever. Okay, great. And then I kind of did that everywhere. So I get a yellow piece sort of over here. Great. But I also get like, I don't know. Yep, that's great. So there's a map I'm claiming from here to here that sort of claps together these things. And to make this sort of a path in the outer space, what I do this is like I do it sort of at time t, I do like t of the folding or whatever fraction of it that I want to do. And as I keep going, I sort of move in the outer space. And that's the idea of a folding path. To make sure that it's a directed geodesic, there are extra conditions that I'm not prepared to tell you about. So instead, I will just say, thank you for your attention.
So the first thing you did was just like and the example you had on the color right now. Is there like an example where you're not seeing the whole?
Yeah. It's okay, so it's the same example, but you just go up 1 rank. So for a so for F3, graph is in the image of the outer space of the free product of the cyclic of order 2. I guess 4 is not so many. I could have written it out. If it admits a hyperelliptic involution. And what this is this is an involution, first of all, which acts by -1 on the homology of the graph. So it's really inverting every cycle, a hyperelliptic involution. It's not hard to see that such a graph is always planar. So as soon as you stop having planar graphs, or you start having non-planar graphs, is I guess the correct way to say it, which I believe you do for F3, but I'm not sure off the top of my head, then you stop having full image. That's one way to say it. Another way to, yeah. Good question. Is it -2? Is it -2? -3? Dang it. Well, I know for other reasons that this is not, it's not everything for F3 as well, but yeah.
You synthesize the liquid to get something.
Yeah, you got a metric, but it's not geodesic. So yikes. I'm not sure. I would look at Francavilla Martino's metric properties of outer space paper. Yeah, I think they described the failure of geodesicity there.
I was going to say, presumably the example you gave is like away from elliptic. Is there some sort of conceptual reason why I mean, presumably there, we sort of know why that happens in the surface space, but graphy way of saying.
Oh, I see what you're saying. Like why is every rank 2 graph hyperelliptic? It's a tropicalization of a. I don't really know beyond that. Yeah. Sort of a happy accident. Yeah. Or I guess you could say like maybe it's like it's a spine for a once punctured torus.
Right.
And the torus has a hyperelliptic involution, and so maybe you could take the spine to be sort of equivariant with respect to that. That's maybe a less silly way to, yeah.